So, welcome. Good to see so many of you hanging around. This is just the end of the day. I'm Shayon. I'm a principal Postgres specialist at AWS. Been there almost, this is my 8th year, and we were just having a conversation. A lot more hair back then. This was when I started. A lot of white hair now and beard, but the learning still continues. The migrations are still a very hot topic. So over the years, I've seen a lot of Oracle to Postgres migrations. We've done like almost, I think, 20 plus in the 7 years that I've been there. Just been like a lot of hands-on with customers, small, large, you name it. So these are also a lot of the lessons learned, more practical tips and tricks. And common questions that we get a lot from customers is how do we replace X in Oracle versus Y in Postgres whenever they're moving over, right? So the whole goal is to kind of see how close it is or how different it is. So let's get started. So let's see. I've just classified these into like 5 high-level sort of topics. We'll look at why customers are looking at migrations in the first place. Then replacing specific features. We're not covering everything under the sun. There's a lot. But at least this, the most common ones that I get a lot from customers, pretty much like on repeat. Then a few HA solutions, and these are again in no particular order. So just feel free to kind of take it wherever you want to. Stop me if you have questions. And I would be happy to like answer as much as I can. And we'll look at extensions and extensibility of the Postgres database itself, which is quite a whole new topic in itself. And then practical migration strategies, which is more like a checklist of things before you start to migrate. So I always like to kick it off with this because it's always a myth as painted by a lot of vendors. And whenever sort of you get into these customer conversations, you get to like see the picture that it's not really a push button migration. Nothing actually works like this in reality. And there's just sort of the ideal, this is the ideal state of how we would like things to be. But even with like advancements and Gen AI and a lot of sort of work in this field, it's still not as straightforward as some vendors make it out to be, right? So this is kind of addressing those right off the bat. So what is the opportunity? So it's usually a journey, and some of the common sort of motivations that I've seen amongst my customers have been a lot to do with cost at the end of the day. 2025, it's still a hot area to optimize on cost. There are licensing terms and agreements which people are not really familiar with, that they are getting charged, especially coming from Oracle. And it's not as user-friendly as it appears to be, like right on the surface area at least. There is a fact set, there is a sheet of detailed sort of billing that you get as part of the audit, which is kind of a sticker shock to a lot of customers. So price is the #1 motivator in most cases. But then why Postgres as a target is primarily due to the open source community behind it. Right. Prior to AWS, I was part of Vertica, which is again it used to be a startup. It got acquired by HP, which was again a data warehouse based on a fork off of Postgres. And I used to go to these conferences like right out of the grad school, and I used to feel very welcome because I used to meet quite a lot of contributors at AWS and EDB and other companies. And I just used to get like the feeling that this is a very familiar territory. People are here to sort of welcome you. They're very warm and sort of, even if you don't know anything about Postgres, they're willing to kind of get you up to speed very quickly, right? You just have a coffee chat. You just get like a casual sort of conversation. So that kind of piqued my interest. I started learning a little bit. The docs were amazing. The Postgres docs were amazing. Very well laid out, very clearly structured. And built on top of that, there's also the modern development practices around it, right? So containerization, Kubernetes, K2, there's a lot going on. And for all these sort of even EKS, ECS, Fargate, et cetera, the de facto database of choice is usually Postgres. They're not looking at like Oracle. They're not looking at MySQL. Yes, MySQL is great for maybe like a WordPress static website, but not really for mission-critical transaction workloads, right? So those were some of the common motivations. But then as you start sort of getting deeper and deeper into it, there are always a lot of challenges. There are feature differences. There is code compatibility changes. Oracle uses PL/SQL. Postgres uses PL/PGSQL, which is very different. Application compatibility. There are Oracle-specific ERP and CRM applications which are oftentimes not directly compatible with Postgres. And there are like vendor certification issues, et cetera, if you're choosing with a cloud-based vendor. So there's a lot of sort of complexities technologically, as well as there are people challenges, right? So if you're used to sort of working on Oracle for the last 20 years, chances are you're so sort of attuned to the high performance and sort of the high availability and the maximum performance of the systems, you usually expect the same thing out of the box in Postgres, and that's what I've seen in customers. And that's usually, again, a sticker shock because that's not true on day one. There's a whole difference and a learning curve on getting to that performance and availability promises that they've been so used to in Oracle world versus what's available in Postgres on day one. So what this leads to is really an opportunity to sort of leverage more modern databases, more modern practices, distributed databases, of course, we'll talk about a few of those. And so sort of these next-gen architectures, right? So now we are hearing all about Gen AI sort of getting infused into databases, which is databases used to be the boring side of the house. Now they're becoming sort of the more interesting parts, right? So, all right, so we'll quickly cover an overview of Oracle. We don't want to get too much into it. It's a very popular database, of course. And it has pretty much like dominated, I think, the database industry for a very long time because in school, we used to also get started with Oracle. We used to do SQL Plus coding. It's sort of the de facto choice for university. Still is. There is a lot of enterprise-ready solutions by Oracle. E-Business Suite, Oracle Fusion, JD Edwards, Siebel CRM, you name it. They, of course, have the cloud offerings as well, which competes with most of the popular vendors today, AWS, Azure, GCP. And they do have like some, they've actually set the standards really high. We'll touch upon a little bit on the rack and data guard, particularly here, plus the partitioning. But they do kind of raise the bar when it comes to really getting that high performance and maximum sort of available architectures. Of course, the licensing model, it's a little bit complex. It's not as straightforward. There are more sort of sessions, I think, during this conference, and which go deeper into like how they charge, et cetera. So it's always known to be a little bit punitive, vendor lock-in. There are always the negative things about it, right? So these are also like sort of the primary reasons for even considering Oracle in the first place. And it's still doing fairly well, I would say, right? So Postgres, again, at this conference, it needs no introduction, but I've been sort of introducing this slide specifically to other folks who are not as familiar, but it is the most popular sort of object relational database of choice, most compatible with Oracle, again, in terms of the code itself, in terms of the semantics, in terms of the stored procedures, triggers, the way it is sort of set up, the architectural differences, et cetera. And it's also very easy to sort of get started, right? So you can actually just download a package from the website. You can get started very quickly if you're used to command line installations, if you're used to Windows-based installations. There are GUI sort of tools available to support your SSMS style of querying Postgres databases or even like Oracle style of querying. So it's very easy to kind of have that familiar territory within Postgres and kind of build upon it. This slide kind of highlights, again, just amongst the community, where does this stand amongst the developer community, the builder ecosystem. DB engines constantly sort of, we've seen steady growth. You'll see that orange line kind of growing steadily over the years. Postgres is there, top 4. But Stack Overflow developer survey on the right, Postgres is sort of the most popular amongst the developers. It has like almost, I think, 50% popularity amongst the developers. All right. Architectural differences. Or really, this was my question, right? Is it really that different? So let's actually dive deeper into this. So we'll compare and contrast on the left and right. Fairly standard Oracle architecture. I'm sure like almost everyone would be familiar, but for those who are not, this is sort of an instance and storage-based model. It follows every sort of architecture, whether it's on the cloud, on-prem, on a self-managed or fully sort of managed, doesn't matter. This will be sort of the architecture model. You'll have an instance which runs a whole bunch of things, and you have the storage in the bottom which runs another set of things. The instance is responsible for running the database processes, right? So this is the memory, this is the mind of the database, which is again composed of a few different things. System global area, which has we call it SGAs. This is your shared pool of sort of shared resources amongst the database compute, such as your buffer cache, your redo log buffer, your data dictionary, your library cache, et cetera, et cetera. So these are your memory structures. But then it also has a set of these, sort of you'll see background processes. And that's sort of the pool here in the bottom, in the center, which is your database writer processes responsible for writing logs, et cetera, writing the block and the logs. There is a SMON, system monitor process. There are checkpointing processes similar to, again, Postgres, which we'll see. There's a log writer, archiver, et cetera, et cetera. And then the database storage in the bottom has, of course, the sort of the physical files, right? Database, again, a container for files. So we have the data files, we have the control file, we have redo log files, we have archived sort of log streams, et cetera, all sitting in the database storage side. Now, compare and contrast this with Postgres, you'll see a lot of similarities. You'll see the buffer cache term being used a lot. You'll see background writer, wall writer, checkpointer, all sort of occurring commonly. The fundamental difference here is Postgres is a per client application single process model. Every client application that connects to the database spawns its own backend process, right? So you'll see why very quickly Postgres gets very resource intensive in terms of sort of hogging or blocking a lot of CPU on the system, because each connection that you open occupies CPU, it occupies memory, it occupies networking resources, etc. So, and there are like better sort of ways to manage it, but default, the open source community code today, the way it works is you have this application, client application, anytime you connect, and you connect via certain different ways. You can have the de facto standard is the libpq protocol, but you can also use JDBC drivers, you can use ODBC drivers to connect. And every connection there, think about like a web app, every session that you open in those multiple tabs, each of those is actually spawning a background process in its own. Right, so it becomes very expensive very quickly in terms of the resources. And that's the fundamental difference. Oracle doesn't do things that way. There's a background sort of shadow thread you'll see which spawns up anytime a client process comes in. Whereas in Postgres, it's a little bit different architecture where it's a process-based model. The other things are same, more or less. You again have, based on, again, a fully managed versus self-managed versus the vendor that you choose to go with, you'll have an instance and a storage-based model. For example, in AWS and RDS, we have a compute for EC2 with RDS Postgres. We have database as EBS. Whereas in Aurora, we have a completely decoupled compute and storage. And again, the storage is shared storage. So vendor to vendor, provider to provider, it'll differ. But fundamentally, this is sort of the overarching technology, overarching architecture that actually governs the way the database functions. All right. So now let's actually dive deeper into the features themselves. So right off the bat, BI applications, reporting applications, ad hoc read requests, materialized views are very handy. And a lot of the times I get this question, how do I sort of replace this when I'm migrating to Postgres, right? So very simple query. I've made it like a little bit simplistic just to understand. There are a couple of like key sort of keywords there. There is a refresh complete on demand. And there are also options to actually do it automatically. You can schedule it. You can do fast refreshes. You can do incremental refreshes. There's a lot you can do with this. So Oracle definitely is, I think, a little bit ahead in terms of the way the flexibility exists today for materialized views. And anytime you have sort of a query rewrite, which probably you got a batch load and that updated a bunch of rows in the table, you want your materialized views to also reflect that, let's say, some amount aggregated. So with Oracle, what it'll do is it can actually automatically rewrite the query with certain sort of flags, say certain parameters, if they are turned on. You don't actually have to go and manually refresh the materialized views again and again. Whereas Postgres is getting there. There are a couple of ways to automate it. There's a basic implementation, which is this, where you just rewrite it as is. And with tools today like Aura2 PG or SAT or even DMS, you will actually get a very similar output exactly as that, right? Because this is sort of the basic implementation. It's sort of looking at exact keywords and doing a translation and then giving out that exact SQL to you. This is what you'll get. And usually what you'll have to do is build a manual refresh behind the scenes to kind of automate this and to also like maintain it on an ongoing basis. So the difference is, in this case, is manual refresh only. You are running a refresh materialized view command. And this is also sort of blocking, because what this does is occupy a lock on the table, which is upon which the materialized view is built. So you can only read, but you cannot write to the tables, right? So that becomes a problem. No fast refresh. You just have a complete rebuild of the materialized view. There's no incremental refresh. And there's also no automatic query rewrite. So how do we get better, right? So this is how we get better. So there is, of course, a couple of extensions, and we'll talk about what these are later. But PG cron is an extension which does cron-like things in the Postgres database. So it automates a lot of scheduling, sort of automation around it. You can schedule these refreshes automatically with this extension. And how you would use this in this context is you would build this. So of course, you have to create the extension first, and then you set a sort of schedule in terms of times, in terms of events, etc. The most common is usually like a nightly job or something. And then you'll notice a keyword there concurrently. And that is the non-blocking operation, right? So while that refresh is running, you can still load data into the materialized view. It'll dynamically refresh it. It is a non-blocking. There's no lock on the table. You can do reads and writes. Plus, if you want it to be like super fast and you want like only certain rows of the table are changing, you do this as well. You need a unique index on this table, because you can uniquely identify rows that are getting changed in that materialized view. And if just one or two rows in a 100 or 100 million row table is getting changed, you still account for that fact, because it'll identify those rows uniquely with a unique index. So this is very similar to fast refresh plus the query rewrite capability that we saw in Oracle. And this is how you would automate it. A couple of extensions involved, but then you can very easily sort of achieve the same thing. The next is virtual columns. And this is again, yeah. So multiple will never run, either if you want to run it on different tables. Mm-hmm. It'll not interfere. It'll run its own independent. Yeah. So with the MVCC model, that's the benefit. It's a pessimistic sort of locking model. And the fact that you're using concurrently will sort of minimize the locks. Yeah, whichever comes first will actually overwrite. Oh, it's not sort of reading it's not writing anything new. It's just updating those records, right? So whichever kicked off first will actually read that updated sum first, and if the other one is coming in, and yeah. So the next one is virtual columns. Again, this is usually like a very common use case for this is if you have like a orders table, you have a sales table, you have a retail-based application, and you're calculating these values derived from some other values of the column. So common example is like, let's say, employees table where you have first name, last name, and you want to generate a virtual column as a combination, concatenation of these columns. Then you would, with Oracle, you would use the keyword virtual and generate it always as virtual blah, blah, blah. That basically means that you have no physical storage of that column in the database, right? So this is just a virtual pointer which points to sort of pseudo files which are not existing in the database. It's just a concatenation of the existing rows in the physical file. Whereas, and this actually gives you some sort of advantages with Oracle because it's dynamically computed at runtime. You don't have to wait for the query to finish. It's not stored physically, so you're not occupying physical disk space. And you can, the benefit is you can also index these. So you can make it much faster, performance-wise. Here, you'll see the tax number is actually also getting generated as a salary times something, and then rounded up. All of that is actually sort of a virtual column, right? Pre-compute aggregate of sorts. Whereas in Postgres, you'll see a fundamental difference is the stored keyword. Without stored keyword, it actually won't work. So with all the tools today, it'll sort of, schema conversion, for example, will spit out this SQL as a replacement. And stored means it'll basically store it physically in the disk, right, in the database file. And although it is doing that, it is maintained automatically. You don't have to do a refresh. You don't have to do any sorts of extraneous operations to maintain it. Once it's defined in the DDL as generated always as this column name, stored, it will automatically update it based on updated values in the table, etc. And of course, it can also be indexed in Postgres. Just sort of a little bit of a mind shift change on thinking, like, because it again becomes a little bit surprising on why is my disk usage going up? Why is my, for the same table, if I'm sort of doing an apples versus orange comparison, it's kind of a little bit of a difference, right? Because here you're storing things physically on the disk. All right, this is a hot topic. There's a lot of debate in the hackers channel, if you've been following Postgres hackers. Over the years, it's been there since, I think, 2019. So Postgres version 11 something, it's been going on, right? So time travel or flashback queries in Oracle, very hot feature. A lot of customers use it. Accidental deletes, accidental sort of updates. You want to go back to a point in time, restore the previous version without restoring the full snapshot, which could take forever. So Flashback does exactly that, but you have to have like an undo sort of segment enabled on the table, right? And undo is basically you have redo logs, you have undo logs. This is where your transactional logs are storing the state of the database at any given point of time with a timestamp associated. So you can, as of that previous time historically, or that SCN, which is in the Oracle terms, it's the LSN in Postgres, it's the change capture number, it's the sequence control number in Oracle versus it's the logical sequence number in Postgres. It's basically a point in time to which you need to go back to restore the state of the database, right? So that's what Flashback does. And there's a lot of sort of things inbuilt within Oracle. You don't have to do anything. All you have to make sure is your undo segments are enabled. There is no setup required. In Postgres, it's a little bit different. And there are a few approaches. I'll link it to the GitHub, which I have in the QR code later. But there is the concept of temporal tables, which is an extension, which natively doesn't exist even in the SQL 2011 sort of syntax and compliant world, right? So with this extension, what Postgres, the community did was they introduced a couple of new data types. And there's a period concept. And in combination with period, there's sort of as of system time, which we custom define. That's the for system time as of that you see in the query syntax. So that system time is always a generated column in Postgres. It's been sort of written as part of that extension. And within the extension itself, it's been implemented as a trigger, right? So what it does is basically there's a start time and end time. We call it the row start and a row end. And what that is a generated column of sort of as of the system time now, as of timestamp. And the row end is actually infinity. You can change it, you can customize it within that trigger. But that's the sort of boundary that you're playing with as of system start and end times. So what that does, very simple sort of use case. You're creating a table in Oracle first. There is a ID number, blah, 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 orders table ID item amount. Insert some data into it, laptop and phone. You're updating it. And now you want to see the sort of state of the world prior to that update. So you can do it either via this timestamp method. So there is a unique timestamp, so as of time, where you can use the interval functions, et cetera, or you can go back to a specific SCN, right, the sequence control number. And this will give you the previous state of things. So imagine like a bad actor comes in and drops sort of a few rows, and you didn't know like what that update was. You can always go back and refer rather than like a complete snapshot restore of the entire database. So in Postgres, that's the link to the GitHub. This extension actually enables like temporal tables for you. So what you would have as part of this extension is you would get this custom data type, which is period, which has this system time sort of inbuilt, and the row start and row end, which were generated, pre-generated columns with system timestamp today and now, and the row end is actually infinity, and you can customize it. But the key sort of here is system versioning syntax. So this will tell your DDL that you can now, you have a history table in the background, which is going to track all these changes. This is using the period extension with the system versioning feature. Yep. It's on top of it. Yep. There is a system, there is a version without system versioning, and there's one with system versioning. This is the one with system versioning. The raw one, yeah. Yeah. This is, again, like debatable because it'll give you certain things, it won't give you certain other things, and that's fair. So, but if you want to get to that same sort of almost flashback query-like capabilities of getting back to a system time, point of time as of that date and time, you can exactly query it like this. So you're doing the same changes, you're inserting the data, you're updating it, and you can use the temporal query with system time as of a timestamp, or you can use sort of immutable functions in the clause, in the predicates. The LSN capability doesn't exist. We are not tracking LSNs again with period. The only thing is today you can do like system time, and these could be immutable functions based on time, or it could be a hard-coded sort of time itself. But this is as close as it gets to flashback. Other approaches, because what happens is usually when you're talking to customers, you'll notice that they will throw out flashback a lot, but usually they are maybe even trying to do something like replay the state of a database with a lot of the other things which are sort of propagating with that change. So usually it could be something like replaying a logical replication slot to a previous point in time, or it could be something like a point-in-time restore with wall archiving. So there are a lot of other possibilities that you can do with Postgres that will give you the same or similar features to get that flashback-like sort of feature, depending on, again, versions. But yeah, that's the sort of snapshot of it. Again, a very common topic, partitioning. How does it differ? How is it similar? It's a very hot topic. Oracle has done a lot of work. It's been there for the longest time, I think, even for partitioning. And the number of styles of partitioning that you can define is a little bit more with Oracle today. Postgres, again, is improving with every major release. There's a lot more coming. But it's pretty simple with Oracle, right? And this is usually a surprise, again, for customers, is just the syntax of it. There are things which are assumed will work with Postgres. Sometimes they don't, until you know how they work, right? So it's usually that. And with Oracle, what happens is you basically, here it's a very common example with a range partition, which is, again, a date range. And what we are doing here is an interval-based partitioning. So all we do is have the partition by range sort of syntax. And we just define once what the partition values will be. And based on this, Oracle actually automatically creates additional partitions as data is getting inserted based on the time column. So there's auto-partitioning automatically enabled by default. You don't have to tweak any parameters, do nothing. There's also things like you can add partitions, you can split partitions, you can merge partitions automatically, just with alter table commands. Right? So there's no concept of detach or attach, etc. The other benefit is just the simplicity. You just have one simple syntax. And there's also the concept of global indexes with partitioning with Oracle, which is where you don't have to worry about primary and foreign key constraints and creating individual partition level foreign key based indexes for a primary key foreign key relationship. Whereas in Postgres, it's a little bit non-intuitive because out of the box, there is a little bit more work involved in creating the partitions themselves, because in Postgres terminology, partitions are nothing but separate tables from the parent table. And it's improved over the years. There used to be inheritance-based partitioning. Now it's all declarative with 10 plus versions. But you have to physically, you have to manually actually write these create table child partition of blah, blah, blah for values for X number of partitions, right? So one way to automate it, again, is using extensions. And we'll see why we are leaning towards extensions so much is because there are things that can actually augment the capabilities of your Postgres installation by these extensions. And PG Partman is one such extension. And what it does is it'll help you not only creation, but also maintenance and management of these partitions automatically, the way you're used to in Oracle. The other thing is it's a little bit of, we saw the effort to manage, but the good things are, if you have it set up correctly, I have a very recent customer example where it's actually PG vector-based use case. So they are using HNSW on 1,000 plus partitions for their tables. It's a 5 terabyte table with, I think, 16 terabytes in the index itself with HNSW. And it's a sub-partitioned sort of scheme of things. So you have a project ID, you have a company ID, and based on that, you have 32 companies, so 32 top-level partitions, and those are list partitions. Based on those company IDs, you have project IDs, and those can vary. So you have 1,000 plus sub-partitions, and all of those are based on the project ID. These are hash partitions. So in that case, what they did was create and again, PG vector is nothing different. It's exactly same as regular Postgres. So rather than a B-tree index, now you're creating an HNSW index once per partition, right? So you have those HNSW indexes created 1,000 times for those partitions. You can automate a lot of that. But the previous way of things they were using this global HNSW index for the parent sort of company ID. And with that, it was taking, I think, roughly around 24 seconds for a query to come back, just a few rows, because of the additional planning time, execution time, pruning time, et cetera, et cetera. But with this sort of partition level indexes, they were able to get it down to milliseconds. We are talking about 100 milliseconds or something. So dramatic difference, and Oracle actually will not give you that level of performance, right? The other thing is that benefit. So that's always sort of the how you look at things, how your data model is, how your schema is designed. But there are, again, better things coming with Postgres partitioning. For example, we have now partition-wide joins. Partition-wide joins you can enable via parameters. There is additional pruning capabilities that we are introducing. There's parallel query support, so you can actually do push down parallel for partitions with multiple worker processes and worker threads. So a lot of sort of customizations are possible with Postgres today, which can, in most cases, if not match, exceed the performance of your Oracle partitioning. All right, so that was top sort of 3 features that I get requested on and on and on from customers. Now let's sort of jump topics, and this will be completely different. A lot of sort of mission critical systems based on these. So Oracle has actually, I will be very honest, has set very high standards in terms of their MAA architectures, their maximum availability, maximum performance, with highest levels of data protection modes that they offer. And RAC is sort of leading the front there. You'll hear RAC a lot. Customers are hesitant to move off of RAC because of financial systems, because of a lot of mission-critical systems cannot afford them to go down. So RAC in itself it stands for Real Application Clusters, and it's basically your shared storage architecture. So imagine like a node that is operating as usual goes down. You have another peer node, which is sort of consuming a lot of the changes in real-time streaming replication-based model. And it can very quickly be promoted all automatically to take on the new role of a primary. So, and the client doesn't even feels the impact of it. There's no downtime, there's no reconnect, there's nothing, right? It's seamless under the hoods. So it gives you this sort of, there are key components built into what goes into RAC and how they achieve these things. Grid infrastructure is one, ASM is a big component of it, clusterware. These are specialized sort of software which helps you achieve that availability promise, but it's all at a cost, right? You have to probably sell your liver or your kidney to get to this performance, but it does exist, right? And this helps you with zero downtime upgrades. This helps you with automatic failovers, rolling upgrades, you name it. So a lot of good things with RAC, so the bar is really high. And similarly, if you combine that with DataGuard, DataGuard is where you have your disaster recovery sort of strategies. Your RAC was more HA. So DataGuard, again, is where you can have it as a logical or a physical, where it's more to do with sort of replication. And what you do is you have a physical server, you have a standby server, and you have sort of streaming logs sent to the standby servers at every point of time. There are specific sort of capabilities. You can have a fast start failover. You can automatically fail over to the secondary if you wish to. The standby is also available for reads. We call it active data guard. And it's basically like a hot standby mode in Postgres. There's also things like once you have this failover, failback, switch over sort of capabilities in region or cross region, there is always that role reversal you need to sort of pay close attention to, and the application endpoints that you have to manage with Postgres. Here, it's all automated. You actually get no sort of interruptions. You don't have to manage anything. So there's load balancing, there's business continuity, there's role management, there's querying in the sort of active standby database at every given point of time. You can have a synchronous versus an asynchronous mode, plus a maximum protection, where you basically architect it always up and running in different availability zones plus regions. So this kind of is the sort of the North Star, right, that we want to work towards with Postgres. So given that scenario, let's look at like what Postgres offers. So a lot of flexibility, a lot of architectural patterns, and you'll keep hearing these or seeing these in one or the other cloud vendors. Usually like RDS and AWS RDS or Aurora, you'll see a lot of replication concepts with global database, etc. With similar with Azure or GCP or self-managed, EDB, it doesn't matter. But high level, this is all sort of a good snapshot of what are the various terminologies, technologies. Whenever you hear about like high availability and highly performant, maximum performance, DR sort of architectures. So we'll not cover everything, but let's go over a couple of them, right? The session right before mine was actually Arnab, who's I think not here now, but his session was a deep dive. Oh, he's there. His session was a deep dive in Patroni, and I hope some of you did actually enjoy that session. There was a demo, and there was a lot of good things shared there on the implementation details, etc. But Patroni is really another sort of open source tool. It's available for free, and it gives you a very nicely sort of automated, highly available architecture. There are, again, in the Postgres world, things are like a little bit scattered across. It's not as structured as Oracle, right? So you have to kind of fish around for a few different things, and you have to sort of stitch it up together. So with Patroni, what works is sort of we saw DCS, which was the distributed consensus sort of state of things, which is where you'll maintain things like leader elections And if you're in a distributed world like CockroachDB, etc., you'll have things like raft consensus. So who's a leader at any given point of time, who's a follower or who's a read replica following behind. Those things are where things like console or etcd or zookeeper come in, and they work very nicely with Patroni. And Patroni is basically like a daemon that gets installed on primary and standby nodes, here in this case with Postgres. And along with that, we'll also, you saw the sort of load balancing capabilities with Rack and DataGuard. Here, you'll need like a connection pooler. It could be PG pool, it could be PG pool 2, it could be PG cat, it could be PG bouncer, it could be HA proxy, doesn't matter. Right? As long as you have like a connection pooler to at least load distribute and round robin between which is the active leader node, which is supposed to be my primary, which is supposed to be my secondary, etc., you're covered. But these are all the things which you'll get with Patroni. It gives you that automated high availability and highly available Postgres cluster. etcd is your sort of distributed key value store. Like any sort of key value store gives you that configuration for leader election and maintains the state. HA proxy is the endpoint for dynamically routing connections to the right sort of endpoints, et cetera, et cetera. And there's sort of good monitoring involved, which we probably saw in the previous session, but if not, there's a lot of sort of monitoring and health checks built into the Patroni system itself that you can easily sort of tail it out to log files, or you can also sort of consume those within your own dashboards like Grafana, etc. All right. So when it comes to the managed, I thought like I'll just introduce RDS and Aurora together. So similar sort of concepts, but then when it comes to HA, RDS supports multi-AZ, AZ-A and AZ-B, a primary and a secondary, active passive mode. Multi-AZ cluster mode is a newer one, which actually supports active reads from the standby. And it's based on synchronous replication. You basically are sort of limited by the amount of writes you're making because you have to wait for the commit back. So it's synchronous. Aurora, on the other hand, within a region is asynchronous, and it has, again, a multi-AZ distributed storage. Compute is just one AZ as a primary, but then you can have up to 15 read replicas in different AZs, which makes it highly available. If there is anything wrong with the primary, there's an automatic failover to the replica. It gets promoted as primary. So Aurora HA by default, RDS multi-AZ is active-passive. Aurora is active-passive, but then also active in the terms of reads, read replica. Now, the other one is limitless. So limitless, fairly newer sort of option. But again, it's built within the Aurora family. So I thought might as well introduce this. Anytime you are looking at a horizontally sharded database like Citus or something that actually needs much more write throughput than is being limited by a single writer instance, that's where you basically start to shard things out. And a very common example in the community is, if you've heard of this company called Notion, Notion actually embarked on a massive sharding process over the years, and they were able to like shard on fully sort of self-managed instances based on a shard key. So Limitless Database is our Postgres-compatible sharded solution, which again gives you a lot of good things. It uses sort of our serverless instances under the hood, but very good for achieving that high throughput if you have a sharded schema design, right? Not good for everything under the sun, but just for like sharded applications. The way it achieves HA is something by the concept of compute redundancy. So we have redundancy of 0, 1, and 2. In this example, you'll see basically like a layer of distributed transaction routers on the top, which are nothing like, you can think of these as individual Postgres nodes, which are managing the metadata, which are doing query coordination, which are also routing queries to the right shards, which is the layer below, data access shards. And data access shards will always contain sort of a slice of your sharded information, plus you can think of these as smaller tables which are references. So it contains a slice of the shards plus a full copy of the reference. So you can get to a single shard optimized query, and you're not doing cross-shard joins, right? So that's the whole idea. And with a compute redundancy of 2, your S1, shard 1, is automatically replicated in 2 other availability zones. So S2 and S3, similarly S2 into alternate availability zones, and so on. So this is, again, another highly available architecture. Rep Manager, again, very popular in the community. So primarily for DR purposes. I'm not going to spend too much time, but think of this as your physical streaming replication. So this actually does a primary and a standby with a witness. And the witness actually keeps a track of who's your leader, who's the follower, who's the read primary, who's the read replica, etc. And there are like a lot of, this is again an extension, and there's a lot of tooling available to actually do a lot of monitoring, alerts, failover, switchover, setup, etc. This is a pretty stable project in the community, actively being built upon. Physical replication is where you are doing all or nothing, right? That's the fundamental difference between physical and logical. So Postgres also supports physical for HA. This is native sort of implementation of the Oracle Data Guard replication with Oracle. And the concept is we do wall shipping in Postgres. So your write-ahead log, which is equivalent to your redo logs, will be shipped as is, block by block, page by page, 8 KB page. Every page is actually getting shipped to the standby server. So you cannot do like granular replication. You cannot do selective table-level replication, row filtering, etc., which is possible in logical replication. This is sort of the fundamental difference. Synchronous, of course, the previous one is physical. It gives you the guarantees of strong consistency, whereas your logical doesn't, right? So there's a replica lag always, and that means that you'll always have eventual consistency, right? So logical replication is by the very fact you don't have to do all or nothing. You can be very selective and select specific schemas, specific objects, specific tables, specific columns to actually replicate. Very good for a lot of these use cases like reporting applications, if you're doing sort of table level replication with certain columns for reporting. If you are doing cross-version replication to migrate or upgrade to a different version, very useful to do a quick sanity check. 16, these things used to work. 17, whether this will work or not, you can do a quick sort of replication test. And there are, the whole concept of logical replication in Postgres is built on the principles of pubsub. You have a publisher, you have a subscriber. Publisher will publish changes, which is the log, the wall file. The subscriber is basically subscribed to that service, which is publisher, and it's consuming the changes real time. All right, so that gets us to global database with the AWS stack. And here, things are a little bit different. We use the physical storage level replication within Aurora, which is, again, all or nothing. So it's physical. Remember, physical and logical, that's the key difference. It's all the data that is getting shipped into the primary is getting shipped to a secondary region altogether. So very good for DR. If things have, like the whole region was out, you can very quickly sort of spin up the alternate region as a primary and start your business as usual. We'll not cover too much into the how these things are working, but with global database, what is fundamentally different is you get a set of these additional replication server and agent pairs once per region. So with global database, you can have 5 regions. That means you can have 5 pairs of server and agent in those 5 regions. And these are what is responsible for shipping out those logs from the primary region to the secondary region. And usually, because we are using custom hardware for this, it's physical sort of hardware being deployed to make sure that this cross-network communication happens and everything happens. The replica lag in this case is usually way better than logical, which is less than 1 second in most cases. And now, building on top of this, you might be interested in DSQL, of course, the newest addition to the family. But I sort of found it useful to compare and contrast again with Postgres, regular, how Aurora Postgres works, versus DSQL, which is, again, in preview today. It's the CockroachDB equivalent from Aurora or AWS. The way this differs is a little bit sort of interesting. So you'll see on the left, Aurora Postgres is 100% Postgres compatible. Aurora DSQL is compatible, or it's a version compatible. It's basically now the preview is based off of version 16. And even off of version 16, not all the functions, not all the data types, not all the extensions that work with 16 will work with DSQL. Because it's, again, based off of the same query optimizer, same query syntax, same sort of planner stats, etc., of the Postgres engine, but it's re-architected in a distributed, completely net new way, right? So things have been completely rewritten, and the way they've been rewritten is like this. So with Aurora on the left, you'll see 3AZ default distributed highly available architecture. And whenever we talk about like data, it's the log and the blocks, right? So with Aurora. What happens is your applications in, let's say, first AZ comes in. Aurora is a single writer architecture, right? There's a one writer in region or globally, doesn't matter. This is in region first. So we have a read-write instance to which the app connects, does its reads and writes. The way Aurora is different is there is no engine checkpoints. You don't have a wall writer. It's basically the log that is getting flushed down to storage. There is no full page write, so it gets you better performance. But then anytime you have another sort of application coming in and doing writes, you need to still be bottlenecked by that single writer instance. DSQL is more truly active multi-writer architecture. You have individual Firecracker VM nodes, which is again serverless, and it gets spun off basically as a query comes in. It's dependent on the number of queries that are getting initiated. As a new query comes in, a new VM, sort of a Firecracker VM gets spawned, and you get a completely net new read-write instance. And that is, again, writing to the DSQL distributed commit log. This is, again, distributed across regions. This is what we call a journal, distributed journal. So it's maintaining sort of an append-only copy of state of things. And the fundamental difference, again, with Aurora Postgres and DSQL is the locking. DSQL follows an optimistic concurrency model, which is OCC, which is every time you have a commit and there is a conflicting row, maybe from the other writer node, whoever is the first to commit wins by default. There is no locking, there's no pessimistic locking, there's no select for update, the way Postgres does today. So with OCC, what happens is the first commit that comes will win. The second commit that is conflicting will actually error out. So there needs to be a retry logic built in. Right? If you're using, let's say, pgadmin, it'll just time out. You'll have to reconnect and reissue that commit or roll back. So that's the fundamental difference. Read-only nodes, we store the cache, which is, again, basically we do cache invalidation with Aurora Postgres, where we don't have to pre-warm the read compute instances anymore. There's a constant stream of changes getting shoved into the read-only nodes, keeping it pre-warm, keeping the read performance up to speed. Whereas if it's not cached, of course, we go to the storage and we read off of that. With DSQL, you'll notice there's no cache. There's no concept of a cache at all. Certain applications which are used to caching, like Redis, etc., we're used to like more frequent key value lookups, the search term, etc., is the exact same. They will not actually benefit from DSQL because there's no caching involved. It doesn't work with a cache. But it is a hyper-optimized storage layer, which is an NVMe SSD, which will give you that optimized read performance, even going down to the storage. Right, so the team has done a lot of work to kind of optimize the way the reads will work, but there is no caching. That's the fundamental difference here. Read-only modes, so anytime you are doing a read in DSQL, we are still spinning up that Firecracker VM, which is a net new instance serverless again. If you're not using it, it'll just shut down. With Aurora Postgres, what you can do is a hybrid configuration, where you can spin, let's say like it's once a day reporting query. You can have a serverless instance, and very recently what we did was launch the complete scale to 0. So what that does is anytime a query is not running, your serverless instance will actually completely shut down after 5 minutes of inactivity. That's the default sort of setting. And what that gives you is better cost because you're not paying for any compute anymore. You don't have to, again, worry about provisioning a new instance for occasional reads. Because it's serverless, it'll automatically scale up when the need arises. But that's sort of the fundamental difference, right? So this is all in region. Active-passive, Aurora Postgres, active-active DSQL. Globally, it's a little bit same but different, I would say. So again, on the top is Aurora Postgres, bottom is DSQL. Top, you'll see we are sort of limited by the region commit latency. That's the benefit, right? Because here, it's not OCC. So what happens is anytime you're doing a commit, it's a single writer which is doing it. So there is no chance of a conflict, right? There's no other writer instance, etc. So anytime you get the latency to get the acknowledgement back from, we do a 4 out of 6 sort of write quorum in Aurora. So from 4 of those, the chances are the time it replicates to the global region will also be in milliseconds. So it'll always be that regional commit latency that you're bottlenecked. That's why it's in green. It's never a problem. In DSQL, you're actually doing a sync on commit. And that sort of elevates the performance, right? So what happens is, or degrades the performance. You have these whole lot of transactions coming in, insert, update, insert, update, insert, update. Then you do a batch commit at the end. The price you're paying for that commit is at the time of commit. Because once you're doing that commit, it'll only ship those writes over to that other region. Before that, those writes are not even visible in the other region. So the reads are local, the writes are global. You're paying for the penalty of that globally replicated write. That's the network round trip, et cetera, et cetera. That's always sort of the consensus algorithm. It's always in these globally distributed architectures. So the price you pay becomes your cross-region network related more rather than anything else. And if you're in US East 1, US East 2, or even the West Coast and the East Coast, US East 1 and US West 2, the latency is much sort of lower because you still get like millisecond. But if you're talking about like Frankfurt and Asia Pacific, that sort of exponentially increases. All right. We are almost done, I promise. I'm not going to hold you longer. Extensions are, again, a fantastic sort of offering from the Postgres community. There are over 1,000 today in the community. Fundamentally, what these are libraries or helper functions written on top of the core Postgres C language without actually forking the code. So they're not disrupting anything in the core libraries. They're just enhancements or feature sort of additions on top of your core Postgres code. That will work as is with the Postgres libraries. So common ones are PG vector, PG stat statements for monitoring, PG crypto, PostGIS for geospatial, et cetera, et cetera. RDS and Aurora supports today, I think, around 92-ish extensions. We are adding more and more. But there are like a whole range of like security-related requirements, et cetera, that it needs to go through. This was from Timescales. They do a survey every year. So the state of the database, sort of just to get a community sense on what's resonating well, what's not resonating. So a lot of questions there. I've sort of linked it there. Very interesting report. 50,000 plus sort of surveyors. And you'll see what is your favorite Postgres feature and what are your top 3 favorite extensions. Extensibility is the number one. Again, from Oracle, coming from Oracle, it's the number one thing that customers use and request. And these are some of the more common ones, which is, we've already talked about. PG stat statement is more for monitoring, PG partment for partition management, PG vector for vector search, et cetera, et cetera. PG vector, again, I like to sort of show this slide a lot because this is sort of one of the extensions where there's just exponential growth. It's a meteoric rise, like a hockey stick that you've probably never seen in an extension in the community. But as of this morning, I captured this about like 15,000 stars on the GitHub repo. This is from star history. And you can see like a lot of comparisons being done against like other purpose-built vector databases in terms of the favorites amongst the developers. So some of the key ones for Oracle users, categorize these into like high-level buckets. HAN replication, these are the ones that come up the most. Rep manager, that's the one we saw. PG logical is again a way to do logical replication via an extension in the community. You don't need to, you don't have to, because natively there is a pub/sub model built into the code, and it's just getting better day by day. But PG logical the open source version was maintained by Second Quadrant, now sort of Enterprise DB, and it gives you a little bit more flexibility in terms of the conflict detection and resolution capabilities. So there's things like BDR, bidirectional replication, that you can do with a little bit more granularity around conflict management. Natively, logical replication doesn't support as much conflict resolutions. PG Active is available on RDS Postgres, which again gives you active-active multi-node sort of globally distributed. You can do active-active across different regions, different writer setups, etc. Similar to like Golden Gate, right? So, but not as close as performance. Performance is still a little lagging. Others are more sort of maintenance and management and some utilities around functions, like Aura FCE is for your Oracle equivalent functions and sort of core capabilities, decode equivalent, NVL, replace null, if, etc., dual system tables, etc. The other ones are, the ones that I've seen a lot are the Aura sort of FDW, the Oracle FDW, which is a foreign data wrapper, which basically gives you the DB link capability. So you're able to query remote servers from your local servers, and you can do things like predicate push down locally to get like better performance. And the other sort of lesser known use case for Oracle FDW is data migration, right? Because now you can actually do insert into a table, select star from those Oracle tables. It becomes a very neat hack to kind of get your data very quickly from Oracle to Postgres. Similarly, for Postgres FDW, you can do like push down with Postgres remote tables, etc. There are sharp edges. Postgres is not perfect. No database is perfect. So there are things around, if you're looking especially like at multi-tenancy, so Oracle gives you things like pluggable databases and container database architectures, which is still sort of not replaceable directly. There are resource governors or resource managers available in Oracle today, which is missing in the open source community Postgres, which is more around workload management and per resource sort of query tuning, etc. Partitioning is definitely much more mature, but Postgres is catching up. And a lot of the common sort of complaints have also been around the AWR and the ASH reporting, right? So usually the AWR stats are very granular, very accurate, very detailed, and they can help you in a lot of query debugging, troubleshooting. There are sort of tools available out there for Postgres, like PG Collector is the one we've used a lot. Open sourced, it's on GitHub. It's available as a downloadable sort of file. And it gives you this nice HTML report of all your usage and stats and inventory of your Postgres schemas, databases, objects, etc. There is a company called PG Analyze who've built a whole bunch into like monitoring and real-time sort of SQL profiling for Postgres. So that's, again, a very good one. But still, like, there are some gaps, which I'm sure like these are getting looked at by the community. Migration strategies we won't cover as much. This is just a checklist. You don't have to like really, this will again vary from customer to customer. You will sort of see this. You can start here, but then you have to customize it, tailor it per the industry, the compliance requirements, the regulated requirements, etc. Tools a lot, and a lot of those are actually free. So Aura 2 PG is a very popular one. Not only does schema conversion, but also data migration. AWS schema conversion tool, now sort of part of the DMS service, gives you a free assessment report that you can share with your teams, etc. Gives you like the level of complexity and the level of effort required to convert your Oracle schemas, data types, objects, stored procedures, foreign keys, triggers, etc. to Postgres equivalent on the cloud, of course. And then Postgres FDW, we saw the Oracle FDW way to migrate things. There's also a lot of logical replication-based tools, such as Debezium, or you'll see Stream, which is, again, a very popular one. Fivetran is actually another company that was, I think prior to that, it was, HVR, exactly. HVR used to be a very popular one in the community. Matillion, Pentaho, Talend, Airbyte, there's a session, I think, tomorrow. A lot of these ETL tools will also do a lot of transformations on the fly to kind of push data into Postgres. And you can do things like cascading replication, and you can fan out like one-to-many and so on and so forth. So where is the road ahead? What is the recap? What is the key takeaway? So Postgres is definitely, I think, the choice these days. A lot of customers, primarily, again, reasons that we saw, there is always at least one, if not many options, alternatives available with Postgres. The way Oracle has sort of set things up, there is a high bar, but then Postgres is not far behind, and there's a lot of innovation around these specialized cloud vendors, particularly. And yeah, these are the things that we covered. If there are more topics, please feel free to sort of talk to me. We can meet at the reception. But if there are any questions, I'm happy to take it. With that, I'll sort of wrap it up. Thank you for your time. Yes. Mm-hmm. I don't think so. So it's definitely here to stay for a little bit. The thing is, like, customers, the way like Oracle has set things up, it becomes very hard to just remove everything, like at least for the foreseeable future, because there are like mission critical systems being built on top of it. And especially with the promises of the sort of latencies and the guarantees of uptime, the availability promises, it becomes very hard to, like, any customer will not actually risk moving off completely, at least in the foreseeable future. There is still, like, I talk to these customers a lot. Within Amazon, within AWS, Amazon is actually still a very large customer internally, where they still have the financial transaction systems on Oracle. They did a big bang migration, and Jim actually talked about it this morning, about like, I think 70 petabytes and 7,400 databases off of Oracle to Postgres over the course of 3-4 years. They are still maintaining some of those payment systems on Oracle today, which is again on-prem. So they're not even like willing to move to a cloud provider because of certain promises, certain guarantees to their customers around things like highest availability, highest performance, maximum protection, et cetera, et cetera. And there's also sort of the inherent, the aspect of control, because it kind of is a mindset shift, because a lot of, you'll see hyper-perform or hyperscalers, even startups, they like to sort of have control over who's running a process. It shouldn't be fully managed by the cloud. There is a process that I need to orchestrate. I will own this. It should be monitored by our team and not managed by some other cloud provider. So they're also hesitant to let go of that control sometimes. And that also kind of builds into the whole sort of tie-in of Oracle to why they are not able to get off as quickly. And for that very reason, the Oracle database at AWS was sort of brought in, because it's letting customers still be on their, like, for example, especially for these mission-critical Exadata and rack systems, you still are able to maintain that within the sort of data centers, physical data centers, but you are able to leverage AWS infrastructure for the software, for the database compute processes. But you're still, like, data is still residing in those Oracle-based data centers, which is where the guarantee of like durability, the latencies, the availability, the protection modes, etc., all reside, right? So as long as like they're not willing to get off of it, they're willing to pay licenses for those data centers, I think it's going to stay. All right, thank you, everyone. We are going to head to the reception, so enjoy.